Hello and welcome to lecture 5 of this course. Today we're going to talk about linear time invariant systems, and we're going to try and understand one of the most fundamental concepts um, in signals and systems, and this has to be the notion, and this is the notion of a convolution integral. We're working on chapter 2 of your textbook, and in particular we're going to work on section 2.3. Okay. Um, As a quick recap of where we've been talking about linear time invariant systems, right? A linear time invariant system, or an LTI system, okay, has an input, we denote it x of t, and has an output y of t, right? And this system has three important properties, right? First of all, it follows the scaling property. So if I double the input, okay, it doubles the output. It has the additivity property, right? What that means is if I have two signals x1 and x2, the response to their sum is going to be the sum of their individual responses, right? So that's the additivity property. The other important property is that the system itself does not change, right? It's time invariant, okay? That means that if I shift the input in time, the output will be the exact same thing, just shifted by the same amount in time. Okay. Now this combination of three properties makes for remarkably simple analysis of equally remarkably complex systems. So in real life, you're going to encounter systems that may not be exactly LTI, but you know what? If you can approximate that system where, to a decent extent by an LTI system, then it becomes much easier to work with. You can analyze it and you can learn a lot about it. You know how it will behave under different kinds of inputs, right? So let's get going. So before we talk about the properties of linear time invariant systems, it's helpful to sort of try and recap some of the concepts that we spoke about before, right? So suppose you have a signal, okay, s of t, that's varying in time. This is your time axis, t, and this is s of t, right? Let's consider a signal that's varying slowly. What do I mean by that, right? What I mean by that is that if I were to consider a point in time, okay, this signal does not have a sudden jump at this point. That's all it means, right? So if I consider an infinitesimal neighborhood around it, okay, so if I have a time tau and I look at, an interval like tau plus epsilon, okay, and tau minus epsilon, right? So over this interval, the signal is not showing a sudden jump, right? It's smooth. What that means is that over this little interval, the signal can simply be represented by s of tau. Okay, it's a decent approximation because over that interval, it has changed very little. Now that doesn't mean the signal cannot change fast, right? So we're talking about slowly changing in the calculus sense. That means it has a finite slope. That's kind of what we're talking about, right? It doesn't have any crazy jumps. So if you have a signal like that, then you can take a snapshot of it by using a function that goes like this. Okay, so you got a step. Okay, and this step function, okay, we're going to call it a delta of t, right? So delta of t has a width of 2 epsilon, okay, and then it has a height of 1 over 2 epsilon, okay, which means that the product of this and this is equal to 1, right? So the area under this curve is always 1. So as I decrease the epsilon, this guy becomes taller and taller and narrower, but the total amount of area under that stays exactly the same. So if I were to multiply this delta of t, okay, with s of t, okay, and look at what happens of to the integral, okay, or the sum of this, right, then what's going to happen is that, at this point here, okay, it's going to take a snapshot of s of t, right? So we want to know what this is going to be, right? So basically over this tiny region 2 epsilon, s of t is going to be the same value that's over here. Let's clean up our notation a little bit, okay? So in order to do that, let me take a fresh sheet of paper and let me sketch it exactly the way I have it on the slide, right? So suppose I have, my sampling function, okay, defined around the origin, okay? So its width is 2 epsilon, okay, and its height is 1 over 2 epsilon, okay, and this is delta of t, and this is time t, okay. Then if I were to take the integral, okay, over any time period that includes this neighborhood, right, we can go all the way to minus infinity, but we don't need to go that far, practically speaking, but what the heck, right? So delta of t times s of t, okay, is going to be about the same as, this is going to be, like the same as minus infinity, uh, delta of t, oh, by the way, dt, okay, and this is going to basically take a snapshot, and this is going to be approximately the same as s of 0, right, dt, right? So s of 0 comes outside, you go from minus infinity to infinity, delta of t dt, and we know this to be 1, right? So this is equal to s of 0. So this is the idea of taking a snapshot of the signal s of t, okay, at a certain point in time. In this case, at time t equals 0. Now, as epsilon is driven close to 0, okay, this guy, so the limit of delta of t as epsilon tends to 0 is basically delta of t. This is the Dirac impulse function, right? And we can sketch it like this. So it goes kind of to infinity, and this is your time t. The important thing about the delta function is that, okay, even though it goes to infinity, okay, its integral stays 1. That's an important thing to keep in mind, okay? We shouldn't forget that. So suppose I were to shift this guy, okay, to a point t, right? Suppose I were to shift this guy, okay, to t, and take a snapshot of the signal here, I end up sampling the value, okay, this will sample the value s of t, okay? The mathematics is essentially the same, it's just a shift of the sampling function. So what this is telling us is that we have the ability to take the snapshot of a signal at any point in time, okay? And we use the properties of the delta function in order to be able to take a snapshot, right? And we can do that for any smoothly varying signal, or slowly varying signal, right? Now, suppose I were to take, okay, let me sketch this all over again. Okay, suppose I have a signal, s of t, okay, and like this is my origin, this is time t, and suppose I were to take an impulse, okay, at t equals tau, right? I'm just picking a number tau, right? Then we can write the snapshot, the same formula that we talked about, okay, as integral from minus infinity to infinity, okay. Oh, in this case I call the signal x of tau on this slide, okay, fine. X of t, okay, delta of t minus tau, okay, is x of tau, okay. Now to also remind you, the delta function is kind of neat, right? When you multiply this guy with anything else, it essentially blanks out this other guy at all points except when t equals tau. Okay? So that's kind of part of the business of taking a snapshot, okay, at t equals tau, right? So whenever you see delta function multiplying something, okay, keep in mind that it's blanking out the other guy everywhere except when t equals tau. So that's another way to think about the snapshot property. So here is a big claim that I'm going to make today, and we'll try and help you understand why this claim is true, right? So suppose I have an LTI system, right? Linear time invariant system. Then here is the claim. So suppose I give you an input x of t, okay? And I want to know what the output y of t is, right? So here is a claim. Suppose I set the input to delta of t, which is the impulse, and this leads to the output h of t, which is a special case of, y of t. Suppose h of t looks like that. Then this is all that I need to know about this system, right? If I know h of t, right, I know everything that can be known or needs to be known about the LTI system. In other words, the impulse response is a complete description of the linear time invariant system, right? This is powerful, right? Because the LTI system could be built out of, say, a whole bunch of parts, right? And think of it as a black box, right? And we don't necessarily know all what's inside the black box. Suppose this is a circuit. I can go into the lab and I can take a signal generator and create a nice approximation to an impulse, pass it through that, see what comes out at the other end, okay? And I have a pretty complete description of what this guy does, right? Of course, this claim only works for LTI systems, right? And this is powerful stuff. So in order to learn more about these LTI systems, we're going to put all three of their properties to use, okay? First of all, what we're going to do is that we're going to take a series of snapshots. So we're going to use the delta function to take a series of snapshots of a signal, right? And for each snapshot, we're going to use this property, right? We're going to essentially, up, find out what the response is for an impulse that's weighted by that snapshot, right? And then we're going to add them all up to compute the total response y of t. Okay, so very intuitive. So we're using all three of the properties for a linear time invariant system in order to do this. Okay, so suppose we have the signal, say x of t, right? And suppose I know the impulse response, right? And in this case, I just drew the impulse response kind of like that, right? Now, of course, in real systems, right, in a circuit, the impulse response is going to live on this side of this delta function because it's these systems are causal, right? So the impulse response that I've sketched here is not causal, but you know what? It doesn't matter, right? What I'm about to describe works for both causal and non-causal systems. Okay, we'll specialize it, but for now, this green line that you see on your left is the impulse response h of t. So if I apply an impulse here, okay, its response at this point is going to be this guy here. That's what we're talking about. Okay. So like I said, our strategy, and I know it sounds repetitious, but I'm trying to say the same thing over and over again for a reason, because I think this concept is important and you need to understand it as clearly as you possibly can, right? So let's try and animate this thing, right? So here's kind of what it looks like, right? So basically what we're doing is that this tau can be varied all the way from minus infinity to infinity. So we can be scanning this function x of t, right? As we scan this function over time, we can take a series of snapshots of x of t. Another way to think about this is that x of t is essentially an ensemble or a collection of its snapshots. It's no different, right? You got x of t, a whole bunch of its snapshots, an infinite number of them. They're essentially the same thing, right? So this is part of this sort of the grand old idea that we're going to be using over and over again. And the grand old idea is that given a complicated signal, right? So you got a complicated signal, and remember I'm using the word complicated and not complex, right? Because the word complex is understood to be, you know, um, in a very specific mathematical sense, right? It consists of a real part, imaginary part, that sort of thing, right? So given a complicated signal, I want to be able to break it down into smaller parts, okay? Each of which is easy to work with, right? We can figure out what it does, and then we put piece of the final answer, right, by essentially combining the responses due to all of these little parts. So if I take a complicated signal x of t, right, I can take a series of snapshots, find the response due to the snapshots, and essentially add them all together to get the answer. Okay, this is the grand old idea that we're going to be using over and over again. Okay, so suppose I have a signal, okay, s of t, and suppose I have a snapshot, okay, at time tau, okay, and I know the impulse response, right? Suppose the impulse response looks like that. So suppose I consider another point in time, time t, okay, the response due to this snapshot. So snapshot at tau, okay, produces response h of this difference, right? T minus tau times, okay, and it's scaled by the value at that snapshot, which is x. Sorry, I'm using x here, so let me use x here. Okay, sorry, x, okay, of tau. Okay, so I'm using the scaling property here. Okay, so I can scale the impulse response in order to find the response due to this thing. So now, if I were to kind of sweep through the signal, x of t, kind of like what my animation showed, right? Then I can basically calculate a series of snapshots. So the total response at time t is going to be the sum of the responses to each of the snapshots. So that is simply, so y of t simply equal to the integral from minus infinity to infinity x of tau h of t minus tau, okay, d tau. And this is easy to understand, right? So suppose I have a signal, and suppose I take a snapshot here, right? And suppose I'm interested in the overall response at time t, right? So this is my tau 1. Then I can calculate what the response at t is. Then I take another snapshot, say at tau 2, and I can sort of calculate its response at time t. I can take another snapshot at tau 3, and I can do the same thing. Since the additivity properties holds, right, I can add them all up to calculate the final answer or the final response at time t, which is y of t. And that's what this formula is saying. Okay, so it's extremely intuitive. So one of the things I'd like you to do is to see if you can arrive at this formula completely on your own, right? So suppose you were to throw away this video, throw away your notes, okay, throw away everything else, and all you have is a pencil and paper. Can you get to this formula? I invite you to do that. And when you do that, you're going to understand what this formula is about, right? And this is going to be an important formula. So this formula, okay, is what we call the convolution integral. Okay, so now in your textbook, the convolution integral, okay, so which is, let me write it out all over again, y of t is integral, okay, so x of tau h of t minus tau d tau, right? So y of t is more simply written as x of t convolved with h of t. Okay, this is the convolution symbol. Now in some textbooks they use a symbol like that. In some other textbooks they use two asterisks. Okay, so you're going to see a little bit of variety in terms of notation, but essentially they all mean the same thing, right? It's a convolution symbol. This is a lot more convenient to write compared to that, because all these integrals and all these things, it's a lot to write. Okay, are you all with me? Okay, so let's continue. So another way to say something I've been saying over and over again is that a signal can be thought of as, an ensemble or even a sum of all its snapshots, right? So suppose I have an impulse at tau, and the snapshot at that time is x of tau, right? And I add up all these snapshots, right? Which means I multiply by d tau and integrate over all this, right? I just get x of tau. This is another way to capture the same idea. Another way to think about this is to say, okay, I get x of t, right? Another way to look at the same thing is say, okay, anything the delta function multiplies is blanked out except when t equals tau, right? So if you apply that, the right-hand side also boils down to x of t. I'm trying to give you a variety of ways to think about the same exact thing, right? Now if I scooch the delta function a little bit, okay, by capital T, then you get x of t minus t, okay, is x of t convolved with delta of t minus capital T. Okay, so another cool thing is that if I take a look at any x of t, right, if I write down another way to write, if I write this same formula down a little bit differently, it's basically x of t convolved with the impulse, delta of t. So if you convolve a signal with the impulse, you get the same thing itself, right? This delta function is a beautiful function, right? It's got these very, very cool and beautiful properties. Okay, so what we've figured out is that in order to find the output, I only needed the input and the impulse response. If I know these two things, and if I know that the system is LTI, that's all I need. I got my output. This is a powerful result, right? It's like power in our hand. That's why I put the picture of the hand there, right? So this is very enabling, because what you can do is that suppose somebody gives you a system. Suppose it's the suspension of a car or some unknown circuit, right? You can say, okay, let me profile it. You take it into the lab, you deliver either an impulse or a unit step, some sort of a test input, figure out what the output is, figure out the impulse response. Now you know all there is to know about that system. So you can now calculate, for example, how the car would go over a bumpy road with a particular kind of bumpiness, right? So you can do all these kinds of cool things just because the system is LTI, right? So this is really, really enabling. A couple of minor details are in order, minor but important. So far we have assumed that the linear time invariant system had a zero input, right? But that's not always the case. So for example, if you have a circuit that looks like this, right, an RC circuit like we've been talking about, right? Now, when you first apply an input, suppose I were to apply an input, which is say an impulse, right? Now there's no saying that the capacitor will be completely discharged. It may have some initial charge on it, right? So that's called an initial condition. So if we know such an initial condition to exist, we can simply add it into the convolution thing. So we can take care of that. Right? We can account for it. Another thing to notice is that the types of systems that we're going to be dealing with in this class are causal, right? Which means that the impulse response of h of t, or rather impulse response h of t, this is t, will always stay on this side of the axis, kind of like that, right? There's not going to be anything on this side. Okay, so on this side it's going to be 0. It means it's a causal kind of system. So for systems like that, right, if I want to find out the response at a particular time t, right, then you only have to integrate from 0 to t because everything before that is 0. So 0 input will produce 0 output, right? Except if there's an initial condition at 0 minus, right? Just before that, if there's an initial condition, we just have to add that, right? So the y of t for such systems, okay, is given by the unit step function, which blanks out everything to the left of 0, okay? Integrate from 0 to t. X of tau, h of t minus tau, d tau, right? If you want to be a bit precise, you would put a 0 minus there. So let's look at our familiar RC circuit and see how it all works out, right? For our RC circuit, okay, we already know, so here's our RC circuit. This is ground, this is x of t, and this is y of t, right? This is R, and this is C, right? So we know the impulse response of this circuit. We calculated that in the previous lecture, right? So h of t is 1 over RC e to the minus t over RC times unit step, okay? And we also had the notation tau c is equal to RC. This is called the time constant. All right, so now let's figure out what the response of this guy, this circuit, is to a unit step. So you want to calculate the step response, or to be precise, the unit step response, right? So now this system is known to be linear and time invariant, right? So it's an LTI system. And check it off, which means we can use convolution. So let's use it, right? So y of t is the convolution, okay, of the input, which is now the unit step function, times h of t minus tau d tau, right? So this is given by, okay, 0 to t, okay, the units. So that's what this guy takes care of, right? So the h of t minus tau is given by 1 over RC e to the minus t over RC times t minus tau. All right, and we got the, and this is multiplying the unit step, right? U of t. Oh, there's a typo on my formula here. Okay, this is, I apologize for the typo. This should be U of t. Okay, so you got U of t, that, but this U of t is just going to be 1 over this range, so we don't even have to write that, right? So we just have to integrate this guy over tau, right? So this is 1 over RC, okay? Now this integral is with respect to tau, remember? So whatever is unrelated to tau can be pulled outside, e to the minus t over RC, okay? Times integral 0 minus to t e to the minus, okay? And then it's like minus of tau, so it's just plus, okay? So it's going to be tau over RC d tau, okay? So let's work out this integral. Okay, so this is given by 1 over RC, okay, e to the minus t over RC, okay, and this integral basically evaluates to e to the tau over RC, okay, divided by 1 over RC, and this goes from this limit to this limit. Okay, now I can directly cancel these two guys, okay, and the answer is e to the minus t over RC times, okay, e to the t over RC minus e to the 0 minus, which is essentially 1. Right, so this is essentially given by 1 minus, if I multiply this out, right? If I multiply this, apply over this, right? So I get e to the minus t over RC. Now this is a fantastic formula because this is what we found out earlier. So this is equal to the y step of t that we had figured out earlier, right? So this is really nice. I'll put a little nice little heart on that, okay, to say this is a good thing. We confirm what we expected. So what this is telling us is that we can use a convolution integral to calculate the response of an LTI system um, just knowing its impulse response, right? We can do that, apply that to any arbitrary input. So to take this insight further, let's now take an even more complicated input, right? So in this case, the input is kind of like a tooth, right? It looks like this, okay? So we have an RC circuit, and let's make our life easy, okay? Suppose for this RC circuit, tau c equals 1. So imagine you have a 1 ohm resistor and a 1 farad capacitor. I know that's ridiculous. The 1 farad capacitor is going to be huge, but you know what? What's a 1 farad capacitor between friends? So let's suppose that tau c equals 1. Okay, keep it simple. And you got a circuit, you got an input that looks like this. So the V input of t, okay, rises from 0 volt to 1 volt. So this is a 45-degree line. This is a ramp, okay? It's just a T kind of thing, right? And by the time it gets to 2, it gets to 0, and then it becomes 0. But even before that, it's at 0. Okay? So this function can be essentially defined in 4 parts. So in part 1, we got, okay, 0. And this happens when t is less than or equal to 0. In part 2, okay, which is this part here, okay, where t is between 0 and 1, okay, this thing is just t. And in this part here, part 3, okay, this is basically 2 minus t. And you can check that easily. So if I stick t equals 1, the output is a 1. If I stick t equals 2, it becomes a 0. Boom, right? So this works between 1 and 2, right? And in this section here, beyond 2, okay, I call it region 4, okay, the output is just, the input is just 0. So if you want to calculate the convolution integral for this, right, we have to basically calculate this over these 4 different zones, okay, or sections, whatever you want to call this, right, or time segments. That would be a technically nice way to call it. Okay, let's make that happen. So for the first segment, the input is 0, so there is no output. Okay, let's assume that our V output, okay, at initially is just 0. Okay, we can make that assumption, right? Although if it's not, we can just add it. Okay, so it's not a big deal. Let's think intuitively about what's going on here, right? So between time 0 and 1, we are charging a capacitor, right? So we expect the voltage, okay? So this is sort of our intuitive expectation. So all the way until 0, there should be nothing going on, right? Now as between 0 and 1, we are charging the capacitor, so the capacitor's voltage should increase, right? So it starts to go up, right? And we reach 1. And after this point, we continue to charge the capacitor, but the charging, becomes a little bit less and less strong, right? But we're still charging it, so the voltage should continue to increase, right? And then we reach 2, and that's when the charging stops, but then discharging takes over, right? So the voltage should start going down at that point. So that's kind of our expectation of what the output should look like. Let's see if we can get that. Okay, so let's load a fresh sheet of paper. So between, time t between 2 and 1, right, the output voltage is going to be integral from 0 to 1 tau, which is because it's a ramp, right, and e to the minus t minus tau. That's our h of t, right? So this is the ramp, and this is h. So this, sorry, h of t minus tau. Okay, plus this is d tau plus integral from 1 to t. Okay, 2 minus tau e to the minus t minus tau d tau. Okay, now if t is greater than 2, right, our output is going to be integral from 0 to 1, the ramp times the impulse response, okay, plus 1 to 2, okay, 2 minus tau e to the minus t minus tau, okay, d tau. Okay, now keep in mind that after 2 there is no more input, right? So there's nothing more to write here because the input is just 0, right? So there's nothing here, right? So if we work through these integrals and plot them, okay, we get something that looks exactly like what we expected. Okay, so the capacitor nicely charges up and continues to charge beyond 1, okay? Remember that. And then after it reaches 2, okay, the capacitor is no longer getting charged, okay, it's getting more discharge, so the voltage just falls off, right? So this is a very nice and satisfying example that shows us that we can use the impulse response to calculate the output for a more complicated signal, okay, or a more complicated input signal. Now we can do the same sort of thing for a pulse, okay? This is another example. So suppose I take an RC circuit, okay, and I apply a pulse, okay, which is u of t minus u of t minus 1, right? Now suppose that in this case our RC, which is tau c, is a half, okay? And the unit for time constant is seconds, so we can write as 0.5 seconds, right? In this case, we know the impulse response. We can reuse it, put that to use. Okay, let's do that. So V out of t is going to be u of t, integral from 0 to t. Okay, V in of tau e to the minus. Okay, let me write it as h of t minus tau d tau. This is u of t, integral from 0 minus to t. Okay, u of t minus u of t minus tau. Okay, h of t minus tau, and h of t is basically 1/2 second, right? Our tau c is 1 second, so 1 over 1/2. Okay, e to the minus t divided by 1/2, so which is same as 2t. Okay, and minus tau d tau, right? So if we evaluate this integral, which is fairly straightforward to do, right, you're going to get a signal Second looks like that. So until the point 1, the capacitor is going to keep on charging, right? If you give it plenty of time, the voltage can rise all the way to 1, okay? But we haven't given that much time. Soon after that, the capacitor starts to. So we get this kind of shark fin kind of pattern, right? Is that nice? Kind of very cute. So again, it goes to illustrate that if we know the impulse response of a linear time invariant system, we can calculate its output to any other input. Okay, so we've tried a bunch of different inputs so far, and this thing continues to work. So what I want you to do is the following, right? I want you to work through each of these examples completely on your own, right? And see if you get the same answers, if you get the correct answers. If you master this very simple RC circuit, right, you're going to have a much easier time understanding the next stuff, where we're going to be dealing with more complicated circuits, more complicated systems and things like that. But you need to absolutely master this stuff, right? And it's so important that I'm taking the time to record this video lecture for you, so that, you know, if this can be of help to you, great, okay? But let me tell you that there is no alternative to a pen and a paper. You really need to sit there and just beat on these equations, work them until you get them clear in your mind, right? So it's only by doing that you're going to actually learn this subject. So to summarize, we have talked about linear time invariant systems, and we kind of showed and demonstrated this claim, right? That for a linear time invariant system, knowing the impulse response allows us to calculate its output to any input, right? This is powerful. This is enabling, right? And you're going to be using this theorem for the rest of your engineering career, right? So try and get a firm handle on it. So what I want you to do is I want you to work through each of the problems that are worked in the textbook, but try and attempt them completely on your own without any help. And then compare your answer against what's in the textbook, okay? If your answer isn't right, try to figure out what you did wrong. Then go back and work it all over again. Keep doing this until you start to get the right answers, right? That's when you know you got the hang of this. Now, for the next lecture, I want you to read through sections 2.4 through 2.5. This is important. This whole chapter is going to be like that, right? If you come prepared to class, you're going to get the hang of this just like that, easily, okay? But if you don't come prepared to class, it's guaranteed that you will not get the hang of this, right? So I really, really, really want you to do that advanced reading that I'm assigning you, okay? This is a serious kind of request for you. Okay, thank you, and we'll see you in the next lecture.